Hello everyone, how are you doing? I trust you're doing great. Today we are continuing with our solving of linear systems, and we are looking at a linear system of two unknowns with infinitely many solutions. So let's get going. Solve the following linear system. 3x minus 2y is equals to 4, 6x minus 4y is equals to 8. So I'm going to start with the method of substitution, then go to the method of elimination, which is what many of you are quite familiar with from high school. Then we'll introduce our raw operations, that is working on matrices, which is what we are introducing to you now. Okay, beautiful. 3x minus 2y. Okay, so I've got my equation 1 here. I've got my equation 2. From my equation 1, I can make x to the subject of the formula there, which is going to give me this equation 3 here. So I'm going to substitute that equation 3 into equation 2, meaning that wherever we have got an x in equation 2, we are going to replace it with 1/3 of 4 plus 2y. All right, so let's get going. 6 into that, okay, 6 multiplied by 1/3, that's going to give me 2. 2 into 4 plus 2y, it's going to be minus 4y, it's equals to 8. Okay, you distribute these two inside here, you're going to have 8 plus 4y minus 4y is going to be equal to 8, which is 8 is equals to 8, which is actually a true statement. I can subtract 8 from both sides to get 0 over 0 here, not 0 over 0, sorry, 0 is equals to 0. Okay, beautiful. So how do you interpret this? What this means when we have a situation like this, it means the two lines, they actually represent the same line. Thus, the system has infinitely many solutions. So we can actually solve any of those two equations to actually get the solution of the system. Right. So, okay, so I've decided to solve the very first one. So we can either solve this in for x in terms of y, or we can do it vice versa, which is what you've seen here. I've actually solved the x in terms of y. So when I've done this, it means y is actually a free variable or an independent variable, meaning that the value for x is actually a dependent variable because it depends on whatever value which has been assigned to y. Okay, beautiful. Since it is actually a situation of having infinitely many solutions, it means to actually make it more convenient or to actually represent the infinite number of solutions, it's actually convenient to introduce a third variable, which we call what an arbitrary value. In this case, I've said let it be t. It can be any, a letter of the alphabet, as long as it is not going to conflict with whatever variables which we have already. All right. So to represent this, okay, cool. So we can now represent this solution as parametric equations. So the introduction of this third variable in arbitrary value, say t, it actually allows us to actually represent the solution of this system in terms of parametric what? Equations. So I want you to see something that we have here. Therefore, this is how the general solution is actually going to look like. So x is going to be equal to 2/3 of t plus 4 over 3. And our y is actually going to be t, where that t is actually an element of what? Real numbers. So how do we get a particular solution or a particular point here, or a specific solution? All we simply do is to assign any real value to t. In my case here, I've decided, okay, what if t is actually 0? It means x is going to be 4 over 3 and y is going to be equal to 0. Okay, this is just one of the many solutions. Okay, beautiful. So I want you to take notice of something here. There are actually plenty plus ways in which you can actually represent this. Okay, depending on which variable you have chosen to be your leading variable. In my case there, I decided to have x as my leading variable, meaning that I'm going to solve x in terms of y. But what if I decide to have y as my leading variable, meaning that I'm actually going to solve y in terms of x? You're actually going to get a different solution there. But be rest assured that all those different parameterizations, they are just describing the same set of points or the same what? Solution set. Okay, beautiful. Having said that, let me look at solving this very same problem using the method of elimination. All right. So this is where we are here, where I'm highlighting. Okay, beautiful. Let's get going. Multiplying equation 1 by -2 and adding it to equation 2 is actually going to give us this, right? So 0 is equals to 0. We know that that is a true statement. And it's actually going to give us a solution. But what solution? Okay, cool. Remember when we talk of a system being consistent, it means it's either it has exactly one solution or infinitely what? Many solutions. All right, so you can see from what we have here that this does actually, it does not impose any restrictions on the given variable, so we can actually do away with it. And then we are actually only going to be left with this, which is exactly the very first equation that we had. So I'm not going to go through this. We have already solved it, right? But this time around, I've actually decided to solve it in terms of y in terms of x. So doing everything that I have, then you can see I've got my x, which is now my free variable. Remember earlier on, it was a dependent variable, but this time around it's a free variable, and my y is now the dependent variable. And this is how you're gonna get what the parametric form if you decide to do that. Okay. Remember, it still describes the very same set of solutions. Okay. As per our method that we used earlier on. Okay. Do I have anything down there? No, okay, cool. That is the statement which I've just said. All right. Now, guys, remember we are introducing you to linear algebra at university level, and we're telling you that all that stuff that you used to do at high school, we can now solve this making use of what? Matrices. All right, so look at this, guys. I've converted the given linear system into an augmented matrix form here, or format, right? So I'm gonna play with my operations, okay? So I need to have a 1 here, and I need to have a 0 here, and I can have a 1 here. You have a 0 here, or maybe leave it like that, depending on whether I'm gonna have it in terms of raw echelon form or reduced raw echelon form. Okay, so solving it using Gauss elimination or Gauss-Jordan elimination. Remember, Gauss elimination, it converts whatever you have been given to raw echelon form, whereas Gauss-Jordan elimination converts whatever you have been given to, when I say whatever I've been given here, remember we're talking about matrices, into reduced raw echelon form. Okay, beautiful. So I have divide row 1 by 3 or multiply row 1 by 1/3 to give us a new one. Okay, beautiful. This is what we have here. Okay, then I want to have a 0 right here. Okay, so if I multiply row 1 by a -6, then add it to row 2 to get a new row 2, this is what I have here. You see, it's taking me to exactly what we had earlier on. So this does not affect, or does not affect, or it's not imposing any restriction there. We can omit it. Now, the corresponding system from this is what you're seeing here. All right. So we can either solve for x in terms of y or vice versa to get the solution. So we have already done that. I want you to take notice of something here. Your row operations, whether you have swapped the rows or you've multiplied a row by a constant and adding it to another, whatever, it's not going to alter the solution set. Your row operations, they just help us to simplify the system and make it easier to solve. That's all. Take note of what I have there. Okay. Beautiful. Right. Let's look at it graphically. Graphically, you see what is happening here. It's like, it appears as if it's the same line. Remember, we've already established that they actually represented the same line. So it's actually two lines which are lying on top of each other. And we call this what? Coincident lines. The lines are actually coinciding, meaning that every point on the other line is exactly the other point on the other line, right? What this simply means that they have the same slope, they share the same y-intercept, they intersect at the same exact points. That, this is basically what it means. When we talk of what coincident lines, there we are, infinitely many what? Many solutions. All right, guys, allow me to do what my mama taught me. A good visitor knows when to leave. Or she would say, a good dancer knows when to leave the dance floor. Adios, amigas and amigos. Till we meet again. Keep shining. Don't do what I wouldn't do, or don't do what mama wouldn't do. Bye.